Section 1.2, Day 2, again, exponents and radicals. We're going to hit the radicals part of that in this video. So I have some definitions for you to write down into your notes. The definition of the nth root of a. So number 1 says if a is equal to 0, then the nth root of 0 is just 0. And for the next 3 examples, I've drawn arrows down here, and I'm also going to show you how to put these into your TIs as a way to help you simplify when needed. So the first one says if a is greater than 0, then the nth root of a is a positive real number. So that with numbers looks like this. The fifth root of 1 over 32 is equal to 1/2 because 1/2 to the fifth is in fact 1 over 32. So to find an nth root of any number on your TI graphing calculator, you are going to, since we want the fifth root, we're going to go ahead and type that number in to start with. So we're going to type in the nth root, which in this case was 5, and we're going to go back into math, down to number 5, which is the x root of. So we've already typed in x, which is the fifth root. So we want the fifth root of, and now we're going to go ahead and type in our expression, which was 1 divided by 32. Notice anytime I have fractions, I'm always going to enclose them in parentheses, and I'm going to hit enter. So the fifth root of 132 we've already talked about is in fact 1/2. We know 0.5 is 1/2, but I just want to show you this feature on your calculator. You can always go from decimals to fractions and fractions to decimals by using the conversion. So again, I just went back into math. I want to know what is 0.5 as a fraction. So I'm going to hit enter, and it will convert that decimal to a fraction for me. Okay, so another nice feature on the graphing calculator. The next example says if a is less than 0 and n is an odd number, then the nth root of a is the negative real number. And this is going to be really important as I get down to my last example here. So with numbers, that's saying something like the cube root of -8 is equal to -2. Again, since -2 to the third power is in fact -8. So it's okay to take an odd root of a negative number and get a real number back. So again, let me show you on the calculator. We could type that in like we did in the first example and go ahead and type in a 3, go into math to the x root of. But if you go into math, notice that we do have a cube root button for you. So we have the square root button is right above the x squared key, and because it's in blue you'd have to use your second function, but we also have a cube root key that we don't have to use, number 5, which is the nth root of any of those. Okay, so if I wanted to use the cube root of, and I wanted to know the cube root of -8, there it is. And my last example now says if a is less than 0 and n is even, then the nth root of a is not a real number. So again, that example looks like this one. So the fourth root of -16 is not a real number. We cannot take an even root of a negative number and get a real number back. So I want to show you what that looks like when you plug that into the calculator. So again, we want the fourth root, so I'm going to type in a 4. I'm going to go into math, down to number 5, and I want the fourth root of -16. And notice how it gives you a non-real answer. Okay, so the fourth root of -16 is a non-real answer. Pretty soon you'll be able to simplify that using imaginary numbers, but right now all you need to answer is non-real for those kinds of questions. Okay, so this nth root is called the index, and the number underneath the radical is called the radicand. So just a couple real quick terms for you. We have a few properties of the nth root. So the first one says the square root of anything squared is equal to itself. Again, the cube root of anything cubed is equal to itself. You do have to be careful with negatives underneath the square root. So the square root of a negative 3 squared is not equal to itself, because negative 3 squared is in fact 9, and the square root of 9 is equal to 3. So be careful with that. So that leads us to this little example here. The square root of x squared is really equal to the absolute value of x, because we want to ensure that what comes out of there is a positive number. So just like the square root of negative 3 squared is equal to the absolute value of negative 3, which in fact is 3. And the laws of radicals, just like in the last video, we had the laws of exponents. The first one says we can take the nth root of a times b, and we can break that apart as the nth root of a times the nth root of b. We have the nth root of a divided by b, which again is the same as the nth root of a divided by the nth root of b. And the last one is the mth root of the nth root of a can be rewritten as m times nth root of a. And before I get into my examples, I just have a couple of big no's, because these have been common mistakes over the years with students. The first one is students trying to say that the square root of a squared plus b squared is equal to a plus b. That is not the case. We can't factor a sum of squares. It doesn't factor as a plus b times a plus b. So do not try and simplify that. And notice the square root of a plus b does not simplify to the square root of a plus the square root of b. Okay, so just a couple of cautionary be carefuls and don't make mistakes. Okay, my first example wants us to take the cube root of 320. So I always want to look at that index, and I want to make perfect whatever it's asking me to make perfect of. So in this case, it's asking me to make perfect cubes. So I know perfect cubes would be like 1 cubed is 1, and 2 cubed is 8, and 3 cubed is 27, and so forth. So we want to look for a perfect cube as a factor of 320. And I know 64 is a perfect cube, because I know 4 cubed is 64. So I'm going to rewrite 320 as 64 times 5. Again, looking for a perfect cube. So the cube root of 64, I'm going to just rewrite as 4 cubed. And we know when we simplify radicals, the cube root of 4 cubed is 4, so I bring that out. I like to cross it off so I know that I've already simplified that. Left underneath are all of my numbers that are not perfect cubes that are left. And so left I have the cube root of 5. So final answer is 4 times the cube root of 5. Letter B is also asking me to find perfect cubes. So I'm going to rewrite all of these as perfect cubes. I know that 16 has a perfect cube because two of the factors are 8 times 2, 8 being a perfect cube. X cubed is already a perfect cube because I can take 3 divided by 3. Y to the 8th is not a perfect cube, but I want to create a perfect cube. So I'm going to rewrite y to the 8th as y to the 6th times y to the 2nd. And we know from our laws of exponents that when we multiply monomials of like bases, we add those, which gives me y to the 8th. So I just rewrote this with the largest perfect cube, because I know 6 divided by 3 will work out nice and neat for me. And z to the 4th is not a perfect cube, but it does contain a perfect cube because I can rewrite z to the 4th as z cubed times z to the 1st. So I've created all my perfect cubes. And now I'm going to simplify the cube root of all of those. So the cube root of 8 is 2. The cube root of x cubed is x. The cube root of y to the 6th is the same as y to the 6th divided by 3, which is y squared. The cube root of z cubed is z. And underneath my cube root then are going to be all of my non-perfect cubes. So I have a 2 left under there, I have a y squared left under there, and I have a z left under there. The next example wants me to multiply these two radicals together. So I'm going to go ahead and multiply. So I have 3 times 6 is 18. A to the 2nd times a to the 5th. When I multiply monomials of like bases, I add those exponents. And b to the 3rd times b to the 1st is b to the 4th. So now I need to make perfect squares since my index is a 2, and I'm asked to take the square root of all of that. So I know 18 has a perfect square, 9 times 2. A to the 7th, I want to create the biggest perfect square. So I'm going to rewrite that as a to the 6th times a to the 1st. And b to the 4th is already a perfect square because I can divide 4 by 2 evenly. Simplify or bring out all of your perfect squares. So the square root of 9 is 3. The square root of a to the 6th is the same as a to the 6th divided by 2, which is a to the 3rd. The square root of b to the 4th is the same as b to the 4 divided by 2, which is b squared. Rewrite all of your non-perfect squares. So I have a 2 and I have an a left underneath there. And then the only thing I need to do to finalize my answer is we talked earlier about taking the square root and ensuring that everything that comes out is positive. So I need to enclose absolute values anytime I have an index that's an even number and a variable to an odd degree, because we want to ensure that this is a real value, and to do that we need to enclose them into absolute values. So final answer. The next section is going to ask us to rationalize a denominator. And basically this is the process of eliminating a radical from your denominator. So you never want to leave, just like you never want to leave your answer with negative exponents, you never want to leave your answer with radicals contained in the denominator. So the first example, I can't leave 1 divided by root 5, so I need to rationalize that. So to do that, I'm just going to create a perfect square down there. So I'm going to multiply the bottom by the square root of 5 to create that perfect square. And again, we know whatever we do on the bottom, we have to do that same thing on the top. So that gives me the square root of 5 divided by root 5 times root 5 is the same as the square root of 25, which we know is just 5. So root 5 times root 5 is just 5. I have rationalized that denominator without changing the value of anything, but just to make that more simplified. Okay, they're going to get a little more complicated because now instead of just creating a perfect square, now I need to create a perfect cube. So I need to ask myself, the cube root of x times what creates a perfect cube? Well, this is 1x, and I know I need 2 more x's to create a perfect cube, so I'm just going to multiply the top and bottom by the cube root of x squared. And again, whatever I do on the bottom, I have to do that same concept up on top. So down below it gives me the cube root of x cubed, which the cube root of anything cubed is itself. And up on top, 1 times anything is that anything. And I now have rationalized that denominator, or eliminated the radical in the bottom. Okay, the next one, I'm going to go ahead and just rewrite this just to hopefully have it make more sense. So again, just like in this example I had to create a perfect cube, and in this example I had to create a perfect square, now here I have to create a perfect fifth. So if I have y to the second already, or I have 2 y's, I know to create a perfect fifth I would need 3 more y's. So if I'm going to multiply by the fifth root of y cubed on the bottom, I know I have to multiply by the fifth root of y cubed up on top. I've now created a perfect fifth because the fifth root of anything to the fifth is itself. And up on top I'm just going to go ahead and multiply those because they have like indices. I can. Notice that you cannot simplify or cancel something underneath a radical with something not underneath a radical. So that is in fact your final answer. Definition of rational exponents. So this is rewriting. So if I have something that says a to the 1 divided by n, that's the same as, notice this bottom number is my index and this top number is really my exponent. So a to the 1 divided by n is really the nth root of a to the first, or the a to the m divided by n is the same as the nth root of a to the m. So again, this bottom number is always your index, this top number is always your exponent. So how would we do something like 8 to the 1/3 on the graphing calculator? Well, we could rewrite it. We could rewrite it as the cube root of 8 to the first, and we know the cube root of 8 is 2. Or how could we just take that rational exponent on our calculator? So again, let me pull out the TI. And to do something like that, you're just going to type in the base. We use this caret symbol right here, so 8 raised to, and when I have rational exponents, I want to make sure I enclose them in parentheses. So 8 raised to the 1/3, which in fact is 2. Okay, my last 2 examples in this video. So here we're going to take everything to the 1/3 power. So we have r squared to the 1/3, and we have s to the 6th to the 1/3. When we have powers of powers, we know to multiply those. So that gives me r to the 2/3, s to the 6/3, which simplifies to just s squared. And the last example, I'm going to go ahead and rewrite to help me simplify this. I know negative 27 to the 2/3 is really the same as the cube root of negative 27 squared. And I know that 4 to the negative 5/2 is the same as the square root of 4 to the negative 5. So I'm just going to show you how you can rewrite those with rational exponents into radical form. I know the cube root of negative 27 is negative 3. I know the square root of 4 is 2. I know a negative to an even exponent is always going to be positive, so I have 9 times 2 to the negative 5 is the same as 1 over 2 to the positive 5. And when I multiply fractions, I can multiply numerators and I can multiply denominators. That's the same as 9 over 1. So 9 times 1 is 9. 1 times 2 to the 5th is 32.